On behalf of the MIT summer session, let me indicate how happy we are to be participating in this edition of the University Video Communications Distinguished Lecture Series. Our speaker tonight is Danny Hillis, a founder and chief guru of Thinking Machines Corporation. He received his PhD from MIT in 1988, but in 1981 he was already becoming interested in the physical limitations of computation and the possibility of constructing highly parallel computers. This work culminated in 1985 with the design of the connection machine, which became the foundation of his very successful company. His topic tonight is connection machine architectures. Danny?
I'm interested in designing computers for the very largest problems. And I got interested in this kind of computer design originally as a user because I had some problems that I was studying in artificial intelligence that required much, much faster computers than I could buy, like 100,000 times faster. And it didn't look like anybody else was going to build them. And so I got interested in the problem of building them. And as it turned out, fortunately, a lot of other people were interested in such computers too. A typical application is, for example, in designing an airplane, people want to simulate the shape of the airplane wing and the air flowing over it so that they can figure out how the airplane is going to fly before they build it and before they have to test it in a wind tunnel. Or another example is the scientists might use it to model a system that they have no hope of really physically modeling. For example, the formation of a galaxy or the folding of a protein. And all of these problems require a tremendous amount of computation, much, much more than we can really do today to do the problems accurately. So it's great for a computer designer because as soon as you build a faster machine, the users of this kind of problem want a yet faster one. And there's really no end in sight for that. They seem to want computers that are certainly thousands of times faster than what we can give them today. Now, another great thing about this set of big users is because they're solving problems that people haven't solved before, they're generally writing their programs from scratch. And they're very often willing to write their programs in a different way to run them on your machine, which is very important because it frees up what's one of the biggest constraints for a normal computer architect, which is to run existing programs. So the computers that I'll be talking about today, which are called data parallel computers, use a somewhat different formalism in programming them, some very different primitives, different programming languages, and things like that. But the users are willing to adopt that different formalism because that's the only way that they can solve their problem. And in fact, as it turns out, it's a very natural formalism for a wide class of problems. So what I'm going to be talking about today is this kind of architecture, which is called a data parallel architecture, of which the connection machine is an example. And I hope, convince you that this is the most natural kind of architecture for very large problems. I'm certainly convinced of that. I'm going to start by explaining why conventional von Neumann machines are a poor fit to very large problems, and why data parallel machines are a much more natural approach. I'm then going to talk about some of the design issues in designing data parallel machines, and specifically how do you achieve a balance between processing and communications and I/O, which turns out to be some of the hardest engineering issues. And then finally, I'm going to talk just a little bit about sort of where we stand today and where this technology is likely to lead in the future. So let me start by talking about von Neumann machines, which are the kind of machines that we're all used to and represent almost all of the computers in the world today. And the basic idea of a von Neumann machine is that you have two pieces. One of them is a processor, which operates on data, does arithmetic, for example, and another one is the memory, which holds data and doesn't operate on it. And so to operate on data, you leave it stored in the memory, you move it across, you add two things together, you put it back in the memory, and so on. And typically, you move one word or a few words across at a time. So this is the single operation model that's sort of implicit in all of the programming languages that most of you are used to programming in. Now, from an engineer standpoint, the von Neumann machine was a solution to a technological opportunity or technological problem, depending on how you look at it, which is that when those machines were designed, the switching components were very, very fast and very expensive, and the memory components were relatively slow and relatively cheap. So it made sense to build a machine that on one side of the room had these big, slow things like mercury delay lines, and another side of the room had these very fast, expensive things like vacuum tubes or relays or something like that. And the vacuum tube switched lots and lots of times for every memory reference. And it worked out very well. In fact, it worked out so well that as we improved the components in that kind of machine, we kept that same basic design. And so if you look on a modern one-chip computer, you'll see on one side of the chip is the memory, and on the other side of the chip are the switching elements, which are the processors. Only today, it's all made of the same kind of stuff, so it doesn't quite make sense to separate them. And in fact, there's a tremendous inefficiency in separating them up, which comes from the use of silicon and the activity of the silicon. So if I take a very, very large machine, remember that's the ones I'm interested in, like a Cray or a big 3090 or something like that, or a connection machine, and I look at what's inside of it. It's all made of silicon chips, and if I lay out those silicon chips, it probably has something on the order of a square meter of silicon in it. Actually, these days it's going to be a little bit more, but something like that. So imagine that I laid out all the silicon, looked at it like that. Now, I would notice that these days about this much of it is in the processor itself, and about this much of it is in the memory system, mostly in the bits of the memory and the memory decoding and things like that. So if I were able to look at this under some kind of imaginary microscope that showed the activity of the chips and showed where useful things were happening, I would see that when this machine was operating, this part of it was very, very busy most of the time. And this part of it would have one memory location being referenced at once. Or maybe if it was a well-pipelined machine, it might have 4 or 5 or something like that. Well, that's a terribly inefficient design because we're, in effect, we're optimizing the activity of this and leaving all this silicon sitting there doing nothing, just kind of holding bits. And in fact, the time that the machine is taken is mostly information traveling from here to there and back again, which is what back is called the von Neumann bottleneck. And the terrible thing about this inefficiency is the bigger that you build a computer, the worse it gets, because the easiest way to build it bigger, the memory system becomes larger, and this proportion of processing to memory gets even more and more out of whack. And that waiting for data to move back and forth between memory becomes more and more the bottleneck at the machine. So it's sort of tolerable when you build a little machine, which has a closer balance of memory and processing, but it becomes kind of intolerable when you build a big machine for these kinds of problems. Now, obviously, the answer is you want to put in more processing somehow. And the general answer is somehow you want to distribute that processing through the memory, and you want to mix up in here processors and memory. And the trick is, how do you do that efficiently? How does it change the programming model? And how do you get it to work? So the von Neumann machine is basically no good for the big problems, and the potential answer is parallelism of getting a lot of things to happen at once. And that will get the efficiency of your machine up. Now, just because parallelism is the only answer doesn't mean it's an answer. And it could be that the problems, in fact, don't allow for parallelism. So there's a real question is there something fundamental about our problems that requires things to be done one at a time, or can, in fact, they be done in parallel all at once? And if they can be done in parallel, where's the big source of the parallelism? Now, if I take a physical simulation example, it's sort of obvious where the parallelism is. Because, for example, imagine that airplane, that you're flowing air over the wing. Well, when the airplane's flying, the real air is computing that in parallel. The air over here is deciding what to do completely independently of the air over here deciding what to do. And so, in some sense, the physical situation is fundamentally parallel. But the question is that reflected in the algorithms? And it turns out that people solve that same problem by a variety of different algorithms. For example, one kind of algorithm, they do it just like the physics does it. They model a whole bunch of particles and model the interaction of the particles as they bump into the wing and bump into each other. And for example, those are called either particle algorithms or cellular automata algorithms. Another completely different kind of algorithm is you model the space as a whole bunch of, as a grid of cells, and you model the behavior of each of those cells by a set of equations that says how the air flows through the cell. Another kind of algorithm is you transform that problem, that physical problem, to a different problem where you have to solve a system of equations, and you solve those equations, and then you transform the solutions back to the physical problem. So there's a whole lot of different algorithms for solving that same physical problem. And it turns out every single one of them has a tremendous amount of parallelism. And the good news is, in fact, it's the amount of parallelism that grows with the size of the problem. So the bigger the problem, the more parallelism there is. So that looks good for the side of parallelism. It looks like maybe it's fundamentally there when you look at the algorithm. But there used to be this thing that would bother people about that argument, which was put most crisply by Gene Amdahl in Amdahl's law. And the argument, and he made the argument that parallel computers will never really work that much. They'll never get you more than about a factor of 10. And here was the argument. The argument was, imagine that I represent the total amount of computation to be done. So that's the line, and here's the total amount of computation. Now imagine that some of it is fundamentally sequential and has to be done a bit at a time, and the rest of it is parallel and can be done all at once. So let's be generous and assume 90% of it is parallel and only 10% of it is sequential. Now, this is how much time this would represent how much time it would take on a sequential machine, because we'll do all of it in sequence. But imagine now I put 10 processors to work on that same problem. Well, I get to divide this part of the problem by 10. So this becomes a tenth the size. And now the parallel and the sequential parts are taking the same time, because the 10 processors don't help me on the sequential part. So I've made the problem a lot faster, almost 10 times as fast. But now let's say I put 100 processors on the same problem. So I now divide this by 100. Well, if I divide that by 100, then I get something which is almost entirely dominated by the sequential part. So I'm getting diminishing returns now as I put more processors on it. So this is a very compelling argument. It's sort of very intuitive that parallelism, even if it works on a lot of the problem, as long as there's that sequential part of the problem there, the machines are going to become increasingly inefficient. And it used to bother me a lot, but then I started noticing, I noticed in my problem it didn't really seem to come up. In my application it didn't really seem to come up. And I started noticing a lot of other people's applications it didn't come up. And I think a lot of people have noticed this these days, that in fact Amdahl's law doesn't seem to be hurting us, and why not? And I believe that the best answer is one that was, I'm going to give a version of an answer that was published by Gustafsson. It has to do with scaling. The answer is people are not trying to solve the same problem on the parallel machine that they solved on the serial machine. They don't want to solve the same problem faster. They want to solve a much bigger problem in the same amount of time. So if we look at, we break up the parallel processing part of the problem, take something like that airflow. If we look at an algorithm for airflow, we'll find that some parts of the airflow problem, or the amount of computation we have to do, are independent of the size of the problem. So let me call that, using order notation, that part is order 1. It's some constant part of the problem. Then there's a part that if I double the linear dimension, I go to twice the resolution, then there's a part of the computation that doubles. So if I parameterize the problem in terms of the number of grid points, for example, and I call that n, then there's a part of the problem that grows as order n. And there's another part of the problem that depends on the boundary conditions and so on that grows as order n squared, and so on. And in fact, there's a big chunk of the problem, which is the relaxation of the interior of the problem, which takes more, not only does the number of points grow up as n cubed, but also the amount of time that you have to relax it grows up as another factor of n. So this keeps on going up, and there's a part of the problem that grows as n to the fourth. So we've got a lot of different parts of the problem like this. Well, what happens if somebody comes along and says, I want a problem that's twice as big. I want twice the resolution. Well, this part of the problem doesn't change at all. This part doubles, this quadruples, and so on, and this multiplies by 16. I end up with a much bigger problem, which goes right off the top of the board. But if I sort of renormalize that and draw it again, it looks like almost all of it is the into the fourth part of the problem. And this stuff is tiny. And if I want it to double yet again, I can make that even more extreme. So it turns out, in practice, when you look at this, and I'm not certain why this should be true, and I'm certainly not certain it's always true, but in practice, these higher order terms are always things that can be done in parallel. So in fact, it's not like there's a fixed percentage of the problem that can be done in parallel, but in fact, the percentage grows as the problem gets bigger. Since I'm interested in the biggest problems, I can always pick a problem that's big enough where it's not where, in fact, that's not a factor. In fact, the customers pick that problem because the customers will pick a problem where it's big enough that that's not a factor. So as it turns out, Amdahl's law doesn't end up biting us, I think, much to everybody's surprise. I was even surprised, and I'm an optimist. So I guess the lesson to learn from this is that the bigger the problem is, the bigger the opportunity of parallelism. And this is one of the differences between designing a machine for the center of the market, say the workstation on your desk, versus designing a machine for these super applications, because they're very skewed in the types of opportunities for parallelism that you have. So the kind of machines that the problems that I'm designing for typically have the opportunity for parallelism on the order of hundreds of thousands or millions of things happening at once. And very, very little of the problem is in this fundamentally sequential part. Okay, so the obvious answer then is I can use lots of processors. And VLSI technology lets us stamp out processors relatively inexpensively, and we can interleave them with memory, and we can build a machine that's all mixed up processors and memory. So what are the design issues for designing a machine like that so that it works efficiently? Well, first of all, notice that the big source of the parallelism is in the data. It's because the data is getting bigger. The size of the problem I keep talking about is really a data size. And so the big opportunity is somehow operating on all of that data at once. Now, that's also very different than a lot of other kinds of parallel machines. A much more normal way of getting parallelism in a machine is to split up the program into several programs which run at once, each of which kind of operates on its own data or some shared data or something like that. But the normal effort involved in making a parallel programming is an effort of splitting up the program and looking for control parallelism. And basically, I think that that's a perfectly good kind of effort, and I think it makes sense. And it probably gets you factors of 8 or something like that. But it won't get factors of 100,000 because you can't break up a 10,000 line program into 100,000 things running all at once that are all different. In fact, the data is growing much, much faster than the program. The programs are pretty much fixed in length. So the opportunity for the parallelism is, in fact, in the loops of that program. And so, for example, take the airplane wing example, or the airflow example. A sequential computer has a big loop that calculates what the air does here, then calculates what the air does here, then calculates what the air does here, and so on and so on and so on. And after it finishes that whole line, it starts the next line and the next line and the next line and so on. Whereas the physical fluid calculates all of that simultaneously. So the big opportunity is in calculating all of that simultaneously. So I'm not so much interested in programs that can be split so that you can run several programs at once. I'm interested in really just running one program. But what I want to do in that one program is I want to take out the loop and do all of the iterations of the loop at once. That turns out to have some great advantages for programming. But I'm going to concentrate mostly on the hardware right now. It also has some nice advantages of hardware. So having done that, so when I do that, that's what I call a data parallel machine. It's a little bit different issue. You hear people talk about single instruction machines, single instruction multiple data versus multiple instruction multiple data. It's a related issue, but it's a little bit different because really SIMD versus MIMD is kind of an implementation issue, that once you've picked a programming model, you figure out what's the cheapest way to implement that model. This is really an issue of what programming model you want to support. And in fact, then you have a choice of whether you want to put some of the control down on the processors or keep it centralized. And that's a kind of engineering issue that just depends on the relative cost of wires and silicon, and probably changes from year to year. So I think a lot of people expect me to defend SIMD machines just because I designed machines that way. I think that was the right way to design machines in 1990. And it maybe won't be in 1995, and maybe it will be again in 2000. It's a small issue. That's not really what I believe in. What I believe in is presenting this data parallel model to the user and doing that in the most efficient way. So how do you do that? Well, the most obvious issue is arithmetic and processing. And that also turns out to be about the easiest problem to solve. So for example, in the CM-2 connection machine, it has two kinds of arithmetic units. It has 64,000 bit serial arithmetic units that are distributed through the memory, and it has 2,000 floating point units, which are 64-bit wide words, which are also distributed through the memory. Then it has some 32-bit data paths for doing indirect addressing and referencing data. So it's a mixture of different kinds of arithmetic units. They're just sort of sprinkled through the memory, evenly distributed to prevent moving data around any more than you have to. And of course, the big issue is not so much building all these ALUs, but it's building a memory system to support them and has sufficient memory bandwidth to keep them busy. Of course, that works out very naturally in a parallel machine because you put each one of these ALUs right next to its own little piece of memory. And so you can read out 64,000 memory bits in parallel and get a tremendous amount of memory bandwidth to keep all these ALUs busy. So it turns out that the peak floating point performance, which is a good way of measuring it, of the machine is on the order of something like 20 gigaflops, which is 20,000 megaflops, which is millions of floating point operations per second. So it's fast, but that's not really a very relevant number because who cares what the peak megaflop number is? It turns out that if I look at this problem, only about a third of the problem is in fact doing that kind of operation. What is the rest of the time spent doing? Well, the rest of the time is spent doing two other major things. One of them is moving data around in communications. And the other one is input-output, things like writing to disks. So I guess one of the points that I'd like to make is that if you're going to achieve this kind of speed up that the revised Amdahl's law promises, you have to do all of the things that you can do in parallel. So if I only did the floating point operations in parallel, then I'm going to get killed by Amdahl's law again because I can only speed it up by 30% no matter how fast I can do those. And in fact, one of the critical things that you have to do, which is much harder than the floating point, is the data motion. Because it's all very nice for the hardware designer to say, I'm going to divide up the memories into lots of little memories, each of which talk to their own processor, but unfortunately, the algorithm doesn't work that way. The algorithm, data has to move all over, and data here has to be added to data here, and so on. So it goes in arbitrary patterns. Now, sometimes those patterns have some locality and some regularity. So for example, if I solved the fluid flow problem over the airplane by dividing up the space into a nice regular three-dimensional grid, then that would work very nicely and neatly if I connected up my processors into a nice three-dimensional grid, as long as it was the same shape as whatever I wanted to solve for that particular airplane. In fact, there's a lot of parallel machines that work that way, and they work very well on that class of problems. The problem is that most of the algorithms are not that neat. And in fact, if I take the implicit algorithms there, where basically I'm working with systems of equations, which have some communications patterns that are kind of all their own, that don't map directly into this three-dimensional space. Or, for example, I might use an algorithm called the free Lagrange method, where I model each chunk of stuff as it flows around, and in effect, I'm redrawing that grid at every time cycle, depending on where the stuff is that's flowing. And there, I really can't even decide beforehand until I run the problem what my communications pattern is going to be. So I need a way of arbitrarily allowing the processors to communicate. And that turns out to be one of the most difficult technical problems in the design of the machine. And there's a lot of different ways of doing it. But typically what you do is you build a physical interconnection network. And on the CM-2, the physical interconnection network is every 16 processors is connected by a crossbar switch so they can all talk to each other, because that's a reasonable number. And then every one of those clusters of 16 processors is on the corner of a hypercube. And they all talk to each other. So that means they each have neighbors in hyperspace. And it's a particular way of wiring them. I won't stop and explain what a hypercube is. It doesn't matter. The point is the programmer never really knows what a hypercube is. And I might design it differently next year, and you shouldn't care. Because basically, the hardware engineer comes up with some neat wiring pattern that they convince themselves is the best in the world. And then the programmer wants to see a model of totally arbitrary communication. So the programmer just wants to say, this processor get that memory location. How do you do that? Well, in the connection machine, the way that you do that is on that physical pattern, you have a bunch of autonomous switches that route messages through that network. And there's different ways of doing that. One way is circuit switching, kind of like the telephone system works, where you call up and you establish a connection between two things that want to talk to each other. Another one is packet switching, like local area networks work, where you put together a bunch of bits with an address on them and steer them to the right place. Well, it turns out that the connection machine uses sort of a combination of those two methods. It actually sends out little packets with addresses on them, but it starts sending the beginning of them before it's got the end of them. So they sort of thread through the network like little snakes. And in fact, sometimes the beginning of it is actually being delivered before the end of it, or before the end of it has even been sent yet. So they're sort of snaking through. And that method of routing, which is used in the connection machine and several other machines these days, is called wormhole routing. And it's a solution that is a very neat solution for hardware designers today. Again, it's one of these things that probably won't matter a few years from now as you get better ways of building switching networks. It may be that a few years from now, for instance, we'll build things with optical technology and the messages will just jump from one part of the machine to another. But the trick is to be able to put in things like that and provide the user with a level of architectural abstraction so that they don't need to know about the details. So the programmer of the connection machine doesn't know anything about wormhole routing or packet switching or single-bit ALUs and 64-bit ALUs, or even really the number of processors that are on the machine. There are levels of abstraction built into the machine, which are the equivalent of things like virtual memory, which provide the programmer with a much clearer model. And part of the trick of being a computer architect is to be able to put in all these kind of messy things that take advantage of what technology you can buy in a given year without providing that messiness at a level that the programmer sees it. So to be able to take advantage of the quirks of technology without messing up the programmer's model. And so I think that the data parallel programming model and the data parallel abstraction of the machine is something that sort of transcends various applications of the machine. So I don't think you should get too hung up with the particular details of how the CM-2 is implemented. Okay, I've talked about arithmetic, memory bandwidth, I/O. No, I haven't talked about I/O. I/O is probably the most neglected part of this equation because fundamentally, most computer designers kind of think of it as not their problem. It's somebody else's. The problem is that the users are not content just to sit there and compute. They want to write down the answer someplace. They want to read in things to compute on. And that means that the machine has to stop and talk to some external device. And typically, computer designers treat that as kind of an afterthought about how to deal with that, because they don't know exactly what the device is going to be, and it's very application dependent and so on. The problem is, in this kind of case where the I/O is actually increasing with the size of the problem, that would kill you if you took that attitude. So you really have to think of I/O as an integral part of the machine. So just as you're distributing processing through there, and just as you distribute communications, and that packet switch scheme, that wormhole routing scheme is a way of effectively distributing communications function through the machine. You have to distribute I/O. So I/O has to come out of that machine, that square meter of silicon all over it, in order to get it out fast enough. The problem isn't just getting it out of the memory fast enough or into the memory fast enough. That's relatively easy because you can just use a lot of wires. And in fact, the connection machine, for example, the CM-2 has 8 I/O channels of 100 megabytes each. Sounds like a lot of I/O, but what do you plug it into? And I would love to just say, well, that's somebody else's problem. But in fact, when you start selling these machines, it becomes your problem because the customer needs to get it done fast. So for that reason, we started solving the problem of building our own peripheral devices, and specifically disk arrays. And so in the connection machine, for example, on every one of these I/O channels, you use a parallel disk array, which does achieve speed by doing a lot of slow things in parallel, just like the machine does. So you put 40 disk drives in parallel, and all that goes on one I/O channel. And when you write a 32-bit word, you write the 32 data bits, each to its independent disk drive, and you write 8 check bits. You compute an error-correcting code and write 8 check bits to 8 other drives. Actually, you only need 7 check bits. The other one is a spare. The advantage of those check bits is that when a drive crashes, which it inevitably does, you still have all of the data because you wrote this check bit, you can reconstruct the entire data even though you're missing any one of the data bits. And the advantage of it is you get a tremendously fast transfer rate. When we designed that, I thought, well, that'll be plenty to keep everybody happy, 40 disk drives at once. But in fact, very quickly, the customer said we want faster. So in fact, the CM-2 today supports, in addition, an idea of disk striping. So in fact, you can run 8 of these data vaults all at once. And so you're using 320 disk drives that you're writing out to at once. And it's very clear in another year or two, they're not going to be happy with that either. So the I/O problem becomes part of the problem that you have to solve, whether you want to or not. And it becomes one of the biggest bottleneck problems in designing a very large-scale computer. And I'm just sort of touching on the bandwidth issues of it. There's a lot of other issues as to how it fits into the operating system and protection and error tolerance and things like that. So I've talked about arithmetic, communication, input, output. What about control? And that's the SIMD-MIMD issue. It turns out that if I look at the control portions of the program, they don't grow with the amount of data. In other words, they remain relatively fixed as the problem size increases. So that means that the control portions of the program are really down in the sequential part. They're not in this parallel part, which means that there's really no need to be able to handle those in parallel for the most part. It helps a little bit, factors of 2 in places. But for the most part, it's not like the control explodes because the control is basically dependent on how long your program is. And the program doesn't get longer just because you had more data to operate on. So that allows the hardware designer to get some efficiencies by taking advantage of that shared control. So the reason that I think that SIMD machines are the most efficient machines in 1989, 1990 timeframe is because the cost of distributing that control and putting it out is too high. It becomes too high a cost. And it's much cheaper to do that control in one place and distribute out the information to the places where it's needed, because you really are only running one program. Now, that doesn't mean that that's the only way to support the data parallel programming model, though. And if in the future at some times you begin to get more and more of the cost of the machine is in the communications rather than in the silicon, because silicon's getting cheaper every year. So it may be after a while that the piece of wire to send the data is much more expensive than just putting a whole other computer at the other end of the wire. At that point, I think it'll make sense to implement the data parallel programming model by putting more control out at the ends. And in fact, the CM2 adopts a kind of compromise approach. It actually has 4 streams of instructions that go through that. So I think that's really the SIMD-MIMD issue. I don't think it's a philosophical issue. And I think in any case, even if you had all this control out there, you really still want to present to the user the model of a single thread of control, because their parallelism is in fact not in the control. Their parallelism is in the data. So that's the control issue. So my conclusion from all of that is to achieve a balanced design, what you need to do is make sure that all of the parts that can be done in parallel are done in parallel in the hardware. And that means specifically you have to do processing, you have to do communications, and you have to do I/O in parallel. And control, you get to do whatever way you think is cheapest. It's just a matter of efficiency. So all of that sort of theories about designing this kind of machine. How well does it actually work out in practice? Well, for many problems today, the connection machine is the fastest machine in the world. And it depends on if the problem is of this sort. There are also many problems for which it's not the fastest in the world. There are probably many problems for which a Cray is the fastest. But an interesting question is, on the fastest problems and the biggest problems, what's the fastest machine in the world? And the answer is the connection machine. Gordon Bell was kind enough to hold a contest where what you did is you clocked machines on doing any real problem, a real application, see how fast they were, how many floating point operations per second. And the connection machine won that the prize this year by a large margin. And in fact, another connection machine program came in second and won the cost performance prize. So it's clear that for the biggest problems and the most data-intensive problems, this kind of machine is the fastest right now. So now what about for the future? How is it going to compare to the competition, which is, by the way, vector machines like Cray's? Well, if you look at the basic technologies that are in the connection machine, they're basically technologies that are improving in cost performance by a factor of 2 or 3 every 2 years. Which if you look at the technologies that are in the vector machines, which are things like bipolar integrated circuits, high-performance cooling technologies, their improvement in cost performance, while substantial, is more like a factor of 2 every 2 years. So it's not as fast. So I'm convinced that not only are these data parallel machines fastest today, but as we look out in the future, they become more and more the fastest machines. So there's somebody who has a pile of money like $30 million or $100 million, make it up, will always do much better if they're solving a big problem to spin that on a data parallel machine because of this increasing spread in the cost performance of the components. So I think the future of these machines looks extremely bright. And in fact, I believe that over the next few years, we'll see machines of this sort, commercial machines of this sort, that are performing regularly in the 100 gigaflop range. Today, they perform kind of in the 5 gigaflop range, maybe getting up to the 10 gigaflop range. But I think that we'll see on good problems performing in 100 gigaflops in a few years. And by the mid-1990s, I think that we'll be talking teraflops. And that's trillions of floating point operations per second. And that's a factor of 1,000 over what you do on a conventional supercomputer today. And so I don't think we yet comprehend how to use it, but that factor of 1,000, one level sounds like an awful lot, but then if I've got one of these problems that grows like n cubed, that's really only kind of that's only a factor of 10 for a problem like that. And if it grows us into the fourth, there's only a factor of about 5 or something like that. So if I want 5 times the resolution, I really want to look at turbulence, I can use up that factor of 1,000 very fast. Or if I want a more accurate model of how the molecule falls, or if I really understand how that spiral arm of the galaxy forms, there's lots and lots of problems that use that up very quickly. And in fact, we're beginning to get hints that we'll be able to begin approaching some of the problems in artificial intelligence that I originally was interested in quite a few years ago when I started getting interested in this type of machine. So we're beginning to see the light at the end of the tunnel, that we can get machines that are really fast enough to approach these problems. So it looks like it's going to be an interesting decade. So let me summarize. The conventional von Neumann machine, the word-at-a-time machine, is fundamentally inefficient for very, very large-scale problems, and it becomes more inefficient as the problem grows greater because of this von Neumann bottleneck. The natural solution is to distribute processing through the machine. In order to maintain a balanced design, we have to distribute not only processing, but we have to distribute I/O and communications so that we can do all of it in parallel. If we do that, then for the biggest problems, we'll be able to do arbitrary amounts of it in parallel. So we'll be able to get very, very good speed ups. And in fact, we can always pick a version of the problem that's big enough so that we have enough parallelism to keep it busy. And finally, the result of all of this is that data parallel machines today are in fact the fastest computers in the world for a class of problems. And it looks like that's becoming more and more true in the future. So in conclusion, I'd like to say that I think this is the natural solution to very large problems. And I hope I've convinced you all that it is too. Thank you very much.
I'm Frank Morris from Petty & Edmonds, New York City. Can you explain to us what advances you foresee in the next few years that will enable you to increase the performance of the connection machine from about 10 gigaflops to a teraflop?
Yeah, I'll speak in very general terms because obviously we're getting into what we're developing in some of our next products here. But fundamentally, there are three sources of speed improvement in the machine. One of them is that the basic technology in the machine is improving. So that's that factor of 2 or 3 a year I was talking about. As we fit more and more onto a VLSI chip, we can get things closer together, actually operate them faster, clock speeds become faster, data paths become wider for the same cost. So there's some things that in a sense come for you for free just from the technology. Another big source of is that we understand much more what we're doing now. So we now have a lot of machines out in the field. Probably about 10 or 20% of the supercomputers that are out there right now are connection machines. And so we're beginning to get a lot of experience in how users actually use the machine and how the machine works in certain cases, where it doesn't work, where the time is being spent, and so on. So another big source is optimizing the machine because we now know what to optimize for. And we were kind of shooting in the dark the first time around. So there's probably almost an order of magnitude to be gained by that. And then the other source of improvement in speed is just plain we'll build machines bigger. And when we first built the connection machine, $5 million seemed like a lot to solve one of these problems. But in fact, these days, people are used to spending as much as $20 or $30 million for a very, very large computer. And so you can just plain old build bigger machines. And that's another source of the power. So if you multiply all of those together, it really is very plausible to get to that teraflop number in the mid-90s.
How much bigger do you see the machines becoming?
I believe that with the way that we understand designing machines now, we can sort of see the next factor of 100 after the teraflop. So, I mean, the designs change, the way that you build the communication networks change, the way that you build the processing elements change. But fundamentally, I think the same kind of architecture and the same kind of model presented to the user will follow through for that kind of speed improvement. I mean, we're talking over the next decade, really, for that. After that, I think even that model begins to fall apart, and it needs something else to come along, some other way of thinking about the problem. Users will have to change all of their programs to get, beyond the, I don't even know what's after a teraflop. But I'm not going to worry about it. I'm worrying about up to about 100.
I'm James Momo from Howard University in Washington, D.C. Thanks for your presentation, especially as you address the problem of time saving for large computation problems. For some of the activities in numerical analysis, we spend a lot of time in I/Os, and I'm looking forward to hear from you what your thoughts are in terms of making the I/O devices more intelligent.
Certainly, people have been talking about for years putting processors down into the I/O devices, in the same sense that in a data parallel machine, you put the processors into the memory. I question in a parallel machine how much is really to be gained from that, because the limitation is really not the data motion between the I/O device and the memory of the machine in a parallel machine. It's easy to build I/O channels to keep up with that capacity. The limitation really is much more in the physical storage medium itself of the I/O device. So today, even the very, very fastest, very most sophisticated computers still use this Stone Age technology of disk spinning around. And that's the thing that's really going to have to change. Now, what's the technology that's going to replace that is kind of the $64,000 question. The optical technology is mostly what's out there now is still disk spinning around. I mean, you're writing things on it with optics instead of with magnetics, but it's still that kind of mechanical motion determines the speed of the system. I think we're eventually going to have to get away from that. Some of the possibilities are things like storing three-dimensionally in crystal lattices. Magnetic bubbles is another thing people have talked about. None of them seem really quite there enough to be able to predict them. But it's clear that we're going to need something like that.
I know that when you do error analysis on a serial machine in terms of different outputs, you have I'd like to compare the advantage in terms of troubleshooting programs that are written in parallel processing, more or less, architecture.
Okay. Fundamentally, writing a program on a data parallel machine is no more difficult than writing a program on a sequential machine, because you only have one thread of control. So you don't have to worry about issues like synchronization or data consistency between processes and things like that. It's things like that where you have multiple threads of control that makes some kinds of parallel programming very difficult. But debugging a data parallel program is really very much like debugging a sequential program and uses essentially the same tools. Now, of course, if the program's doing the wrong thing, then it can do the wrong thing a lot faster, so it can make a lot more mistakes. But the truth of the matter is that it can already make mistakes a lot faster than you can keep up with it anyway. So that difference really doesn't make a difference. Now, that's to do with software errors. Another question which you might have been asking is about hardware errors. And one topic that I neglected in the talk, which is a very big issue for designing these machines, is the problem of fault tolerance. And in fact, the machines that we're designing in the future all have very high degree of fault tolerance, so that one part of the hardware can break and the program continues running and runs. The user sees no error, even though the individual hardware elements are making errors. And that becomes a necessity when you design very, very large scale of machines. And that will become increasingly a problem in designing machines and increasingly a place for architectural creativity.
I'm Mark Tuttle from the DET Cambridge Research Lab. I felt during the talk you were trying to convince me that the data parallel model was the best and most natural model for parallel computation, and I'd like to press you on that a little more. It seems like in discrediting the other models, you're taking advantage of the parallelism that's inherent, the data parallelism that's inherent in the data that you're using, like the airflow over the wing and stuff like that. But it seems like there are a lot of problems where that's not really the case, like chasing links through a semantic net, where you can, of course, formulate that as taking the transitive closure of a graph. And I just wanted to ask you about that.
Well, I certainly believe that other kinds of parallelism are legitimate and useful. The problem with most kinds of parallelism based on control flow is that they don't get you the factors of tens of thousands or hundreds of thousands that you need to really do these very, very large-scale problems. So I guess I feel that data parallelism is sort of the only way that you'll get the speed in very, very large problems. And in fact, the problems that you mentioned, which were database query, computing the transitive closure of a graph, have very, very natural expressions in data parallel algorithms, and in fact work very, very well on a machine like this when the problem is large. So it's not that I think that the other kinds of problems are no good. In fact, I think they're very good. I think multitasking kind of forking parallelism is very useful in many cases. I think pipelining is useful in many cases. I think that those make a lot of sense, but they're not going to get you the factors of hundreds of thousands. So they're really not what you have to focus on when designing a machine that's going to operate in that performance range.
It sounds like you're talking about that's an argument that the architecture that you're interested in is a superior architecture because you can make these chips small enough that you can make these machines much, much bigger. It's more cost effective to make these kinds of machines bigger, but that doesn't seem like it's a convincing argument that the programming model itself is the most natural model.
Well, maybe a better way to convince you that the programming model is the right model is to say that even somebody who builds hardware for a completely different model almost always ends up programming it in the data parallel model. So typically, if you have a machine that has more than a few dozen processors, even if it wasn't designed to support the data parallel programming model, you'll see that the way that people program that machine is to sort of make that machine pretend like it's a data parallel machine. In fact, they only write one program and they run it on all the processors at once. So they hide all of that flexibility that they put into the architecture because they don't know how to deal with it in software. So I think that's a very convincing argument that this is the most natural way of expressing those algorithms.
I'm Karen Matthews from UVC, but Danny, this question is from Gordon Bell. To what extent can we expect a language for expressing parallel computation to span a range of types of machines so that programmers don't have to be retrained?
I think that it's realistic for programming languages that support machines with roughly the same numbers of processors to have the same kind of programming language. So I believe that all machines with tens of thousands of processors will be programmed in the same way by exactly the same programming languages. I believe that machines that have dozens of processors will be programmed in a pretty different way, because there it makes sense to use this kind of fork-join kind of parallelism. And it may be that there's some intermediate stages where machines with a few hundred processors can be programmed in a message-passing way. But I think that all machines that are massively parallel will run exactly the same programming languages. And interestingly enough, they're probably the same programming languages that the sequential machines will run. And that was a big surprise to me.